Welcome back. So it came to my attention that a lot more people want more information about the DMC2, specifically details on certain issues they had when setting it up. Things like setting up the probes. Some people had spindle issues, and some people had questions for me. So I want to go ahead and make a video on that and answer all those questions that people might have. And hopefully I'll help somebody out there that's, beginning to machine and beginning to understand how to use this machine. I apologize in advance. It's currently snowing and it is pretty cold in the garage, and I have my diesel heater on, so there is a bit of background noise. So I do have to put a disclaimer in this video because I'm not going to be covering every single detail in this video in terms of, software configuration or assembly. I'm just going to be covering things that need more detail. I want to fill in that information gap that exists between you assembling this yourself and what Omar has provided in terms of manuals and videos. I want to help out those people that are, stuck on things. And I noticed this especially when I was assembling things and I was configuring things that, I wish there were more information on those types of things, and we'll get into those things. But that being said, I am going to be skipping around a lot in this video, and so please feel free to also skip around and find whichever section interests you most. So the first thing I want to get out of the way is probing. Now, we're in the main screen right now, and if we go into the probing tab, you'll see all the different ways we can probe stuff. So immediately, if you load this up and go immediately to probing, and you click on one of the buttons and you put your probe in, it will not work correctly. So obviously that's because the code associated with these buttons that you're using is not correct, is not set up. So in order to set up that code properly, you have to go up here to Operator and then down to Edit Button Script, and then you will have a chance to click on any button you want to modify at this point. So let's just say this top one, and then a window will pop up. And then here you can see all the code associated with probing for that specific direction. Now, out of the box, like I said, this code will not work. So what you need to replace this code with is what Omar provided you in your DMC2 folder. If we minimize this, that would be right in here. So this is my DMC2 folder, and you can see we have our scripts here: bottom script, left side script, we have right side script, tool height script, top script. So all of these text documents are different scripts for specific buttons. And if you say open up like the top script, you open up the top script, you'll see something like this. And this is the code that will work. So you have to copy all of this and paste it right into here. So once you have the code copied over, you should see something similar to this, depending on which button you're editing. And you have both metric and inches here. So metric is up here and inches is down here. All you have to do is fill in the variables as you see fit. And you can also test it while you're doing this, and you can see exactly what they modify. I didn't have to really modify a lot of values in here. So really, once your probe diameter is set, then you focus on modifying your gauge thickness variable until you see that the probing is done correctly. Notice the current value on the x-axis. When I press the probe button, the machine moves to do the probing, and then the value on the axis has changed. Now I can take off the probe and move the machine to the x-axis 0 position, and then check if that 0 position is actually correct or if I need to make any further adjustments. So some people may encounter this situation where their X, Y, or Z limit switch is triggered and they're trying to reset it by pressing the emergency stop, but as you can see, I'm pressing it right now and it doesn't want to reset. So what is going on here? Well, what Mach 3 expects from you now is to hit the override button and back the machine up from the limit switch. However, to get to the override button, you need to go to a different window. What you need to do is go into Config, Ports and Pins, and then once you get to this menu, you have to go into Input Signals, and then you scroll down all the way to Limit Override. And you can see right now I have it disabled, and I do not have a pin number associated with it. I also have it as active low, or sorry, I disabled the active low. So what this means is I have to enable the limit override, and I also have to set a pin number to this in order to use it. So typically what I do is I set the same pin number as the e-stop. Now, you're not supposed to do it this way. This is incorrect. However, because of the board that I'm currently using inside of the machine, it does not support additional pins to use for the limit override. So I have to assign this to something in order to use it, but I do not have any extra pins. So I'm temporarily only assigning it the same pin number as the e-stop. This is dangerous. This can be dangerous, but if you do need to move your machine, this is one way of doing it. Maybe don't assign it to the e-stop, maybe assign it to like the probe pin or just something different that you can press in order to enable the limit override. So anyway, I do this, I hit apply. Now once I go down here, you can see that the message has changed. Now Mach 3 is saying that the limit override has been activated. You still see that the e-stop is flashing, but since I connected the limit override button to the e-stop, I'm just going to hit the e-stop once again, and now it should clear and stop flashing. Now this is when I can move my machine, and I have to be extra careful to make sure I move the machine off of the limit switch in the right direction. So now I've moved my machine off the limit switch, and now it's important to go back into those software settings and make sure that the limit override button has been disabled, because you want your e-stop to work as it should, and you don't want the limit override on all the time when you hit, the e-stop like I have demonstrated here. So another really important concept to be able to understand is that technically speaking, the machine should never touch these physical limit switches, because the rule being that the machine should stop always on the software limits designed into obviously the software, and not stop on the hardware limits. And so that prevents the machine from catastrophically crashing. These hardware limits, these guys are just the ultimate fail-safe to make sure that the machine doesn't come off the rails and catastrophically, catastrophically damages itself. So one thing that I feel is important to mention here, so people know about it, and especially beginners know about it, is that typically on a professional CNC machine, you would not see normally open limit switches. So you see how the limit switch says NO on the end here. NO stands for normally open. Now, a normally open circuit is typically not recommended for limit switches, because if a wire fails on that limit switch circuit, then the software is not able to tell that the limit switch has failed or something has failed on the circuit. And furthermore, if you have a problem with the machine, right, and the machine is behaving erratically and it's about to come off the rails, you expect the limit switch to be able to stop that machine. And if the software can't detect that the limit switch has a problem, and you expect the limit switch to save you, well, you're going to have a bad time. You see how that situation can be dangerous. Generally speaking, your limit switches on a circuit, on a CNC machine, should be normally closed. So not NO, but NC. So I want to clarify something specifically about the limit switches that I connected over here. So in my previous video, I did mention that I needed to connect these limit switches directly to this board because of some issues with the limit switches. They weren't working correctly. Typically, you would have them connected directly into this terminal block on the board behind here, and then via these ribbon cables, you would then connect those signals, those limit switch signals, over to this board in the front here. Now, I couldn't do that obviously because of the issues regarding the limit switches, and so I said in my previous video that I connected the black or the ground wires to this board. Now, that is misleading, because the way these are wired is this brown wire here is the positive side, the blue wire here is the negative or ground, and this black wire coming off of the limit switch is actually the output wire. And I connected simply all the output wires from the limit switches to this board directly. It wasn't the ground wire that I connected, even though this wire is black. It is not the ground wire, it is the output wire. So you simply connect that output wire directly to this board. If this is still confusing, please look up a wiring schematic for these things, because when I first started wiring these, it did confuse me also. But just know that brown wire is positive, blue wire is negative, and then the black wire is simply the output wire. So some people complained that when they tried to start their spindle, they only heard a whining noise and the spindle itself was not spinning. So I believe that the manual might have been incorrect on the wiring of the spindle, because I think I had the same issue and I needed to rewire this plug basically. The way I figured out the correct wiring was to check the actual connections on the spindle with a multimeter, and I just did a simple continuity test. But I figured that it might as well be beneficial to show my exact wiring on this plug for people that might have issues with their spindle not working. So one of the things I found really useful when setting up the RPM range on the spindle was having a digital tachometer like this. And these are not expensive. This one was, I think, less than 20 bucks. And it's really simple to test the RPM of the spindle by just having a piece of reflective tape on there as it spins. So it's really important to set the RPM range of the spindle accurately, because you don't want your spindle running at 20,000 RPM when you told it to run at 10,000 RPM. But also, you want to be aware of what kind of chip load your end mill is experiencing. Obviously, when you're doing cutting with an end mill, you have some amount of material that's being cut away per tooth of that end mill. So you have some amount of inches per tooth or some amount of millimeters per tooth that is being cut away. And if that's too high or low, you're going to have problems. And that's why it's so important to have an accurate RPM on your spindle. Now, furthermore, you have to listen to the spindle. And this will become more apparent when you have more experience cutting things, but you can absolutely tell when things are not cutting correctly just by the sound of things. And when this spindle was cutting, I noticed it really had a hard time when you set the RPM below 10,000. If you hang around 11 to 12,000 RPM, that is about as low as you really want to go before the torque of the spindle drops significantly. And at that point, you will risk the spindle stalling. And I've actually had that happen to me a few times, because I set the spindle to run at an RPM of, say 11,000 to 12,000, and that was okay for a while, but as the end mill got duller and duller, it created more friction, and eventually the spindle couldn't take a lot of that friction and started getting slower and slower. So you do have to be careful and run the RPM a little bit higher than you think you need to, just because the spindle doesn't have a lot of torque. Now, this can also be slightly improved if you change some settings in the VFD. However, your VFD might need to support some special settings like DC biasing. If your VFD has those types of advanced settings, then you may be able to squeeze a little bit more torque out of the lower RPM range of the spindle, but generally you just want a spindle that is either pulley driven in some way to get more torque out of it, or you want to buy just a better spindle in general. This video is not really going to be about setting up your feeds and speeds and setting up, depth of cut or step over, but you need to have some sort of awareness of like what the limits are when you're cutting certain things. Like, I would never set this spindle or this machine to cut with like an eighth or quarter-inch step over, I generally would stick to maybe a 16th step over or a 32nd step over and run the machine fairly quickly. I mean, this machine was generally built to do high-speed machining. The whole idea behind high-speed machining is that you take lighter cuts, but you do them faster, and so you still have a good amount of material removal. And because you're taking lighter and faster cuts, you're not stressing out the spindle. So technically, it shouldn't stall on you. But still, there is an issue of torque with the spindle on lower RPMs. So I thought it would be beneficial to talk about the concept of adjusting your backlash for the beginners that need to understand these concepts in order to understand how to solve issues relating to slop or backlash in the ball screws. So if you have a nut and a screw, then obviously they interact with threads, right? And inevitably nothing is perfect, and so we're going to have some amount of space between the threads, right? If, say the screw is traveling in a particular direction toward the left, well, all of these threads are going to go to the left, and that space is going to be taken up, right? Once that space is taken up, then everything will move to the left. If everything is moving to the right, then the opposite will happen, and you get all of the space on the other side of the thread taken up before anything will move. Now, this is a very simple concept, but it's important to remember that when you change direction on each axis like this, and when the threads interact, you're losing distance there. So the idea behind removing all the backlash is to have two nuts that are tensioned in opposite directions, so that all of the space on one side of the thread is taken up, and all of the space on the other side of the thread is taken up. And then you have this tension, or it could also be compression, but all of that space is already taken up, And so when you switch directions on any axis, then you will not lose any distance, because that distance is, between the threads is already taken up, is already pre-tensioned. So that is the basic concept behind this, but also remember that if you tension or preload these nuts against the screw threads too hard or too much, then you can increase the friction and the wear of this whole assembly. So do this with care, but this is the basic concept behind not losing any space between the threads when you change direction on any axis. So somebody asked me if I checked my spindle runout, and I didn't in the beginning, but it is important to check. And so checking your spindle runout is pretty simple. You just have to get the spindle running at a slow RPM and get your dial indicator out. Now this dial indicator is has divisions in 5/10,000ths of an inch, and you can see it's barely wobbling. It's wobbling between just one increment, between two lines, and so we can probably safely assume that this spindle has a tolerance of plus or minus 0.5 of an inch. However, that's still not terribly good, because if you're using smaller and smaller tools or end mills, then that runout becomes more and more problematic. So I was also asked if I bothered to tram in the spindle, and I didn't, again, because I guess I was in a rush. But this is, I guess, one silly way where you could do that. I call this silly because, well, you don't typically put your dial indicator in a collet like this. You should have a piece of metal that sticks out at a certain distance, maybe 4 to 6 inches, and then have your dial indicator at the end here. You wouldn't really have a dial indicator right at the center. But anyway, this is just a demonstration. I don't have the proper tool to use it. I would have to either buy or make one. But you get the point that in order to tram in your spindle or tram in your mill, you need to make sure that your spindle is perfectly perpendicular with the surface that you're machining on. And in order to do that, you have to have a way of looking at the imperfections of the surface that you're scanning across. And so that's what this is. That's what this setup does, is allow you to see how perpendicular this surface is and how straight this spindle is. So just by spinning in this small area, I see on the dial indicator that I'm about 0.02 of an inch off. So if you do figure out that your spindle is not perfectly perpendicular with your surface, well, you can fix that by shimming it in the proper direction. And if you don't have the proper shims, you could always cut up an aluminum can and use that. But I highly recommend that you get the proper shims. So, a pack like this is very valuable to have. And maybe this goes without saying, but if you're having trouble with your tolerances on a part, it's always good to just measure your end mill and make sure that your 1/4 inch end mill is actually 1/4 inch. For those people that are interested in looking at my specific Mach 3 configuration, they can do so by looking in my Google Drive project folder. And here you can see all the screenshots I took, and you can look at my specific configuration for my ports and pins, or whatever else that you need. If you feel that something is missing from this or from the video, please let me know in the comments, and I will do my best to try to answer any questions.